Okay, we move on to the discussion of Markov jump process. Okay. If you know something about Markov processes, then a Markov jump process is a Markov process with discrete states and continuous time. Okay. But anyway, I will describe. So here comes the definition. As usual, I consider a physical system with discrete microscopic states indexed by j, which runs between 1 to omega, for example. And then a Markov jump process is fully characterized by a collection of something called transition rate, omega, k to j at time t, which is a non-negative number for any kj which are not equal, and any t greater than or equal to 0. Okay, and so here kj is sort of ordered pair. Okay, ordered pair for any ordered pair kj. I define this transition rate. Okay, and here are just the notations. For each t, the collection of all these omega kj is denoted like this, and the collection of all these for all t is denoted by omega tilde. Okay. And here is the basic definition, the basic meaning of omega. Suppose that the system is in state k at time t. Then the system is in a different state j at time t plus delta t is positive, with this probability. Okay, so first of all, for sufficiently small delta t, this is basically proportional to delta t. So this means that the system jumps from k to j with this rate. Okay, so this probability increases proportionally to delta t. And of course, there can be many. So this takes into the effect of only a single jump or hop. But of course, there can be many, more than one jump. And this, the effect of more than one jump is contained in this order delta t squared. So if delta t is, of course, large enough, then you no longer see this. But anyway, for delta c small, then this probability is proportional to delta t, and the proportionality constant is nothing but the transition rate. I think this is clear. Jump from k to j. Okay, and probably this I should show this picture here. So this is a very, very simple example of a physical system. And so I consider a lattice with 4 sides, and there are 2 particles, green and blue, not green and red. And it seems that two particles cannot live on the same site. And so there are 14 states. And here is an example of transition rate. So in this case, particle can jump only to the nearest neighbor site. So for example, here, this particle jumps from here to here. Then the state jumps from this state 1 to 3. And so the rate of jump is given by this. Or the state can jump back from state 3 to 1, and then this is the rate. Okay, and in this case, there is no direct jump from 1 to 2. So we see that this omega 1 to 2 or omega 2 to 1 is 0. Okay, and okay, so this is a very small system with 12 states. But of course, our discussion is not limited to small systems. So we can consider similar lattice gas system with many, many particles and huge number of omega. And but mathematically, everything is the same as long as omega is finite. And we only consider the case with finite omega. Okay, but this is an easy picture. Okay, so this is something you should have in mind. And here I define new quantity called the escape rate. The escape rate is simply the sum of omega k to j, but I just fix this k and sum over this j. And so the meaning is clear. Okay, so this is a rate of jump from k to j, and I'm summing over j. So the meaning that if the system is in state k at time t, then the probability that it is no longer in k at time t plus delta t is given by this. It's no longer in k because it has jumped to one of these j's. Okay, and again, this is proportional to delta t because the first jump occurs with chance which is proportional to delta t. Okay, and of course, more than jump, the effect of more than one jump is contained in here. Okay, So this is the escape rate. Okay. I think it's clear. And now I'm going to derive something called the master equation. So P of t denote the probability distribution of the system at time t. And the meaning is that Pj of t denote the probability that the system is in state j at time t. Okay. Now I examine for small positive delta t the difference between pjt plus delta t and pjt. Okay. So this is a probability that the system is in state j at time t plus delta t. And of course, this is a probability that the system in state j at time t. And now if you think about the difference, first difference comes from the escape from j. Okay. Initially, you are at j, but within this small amount of time delta t, you somehow get out of j and jumped to your neighboring states. Okay. And this effect is given by this. First of all, you are at this state j at time t. So you have this probability, and you jumped out. And the probability that you go out is proportional to delta t and given by this. And this is a higher order effect. Okay. And so this is the contribution from going out. And of course, there are processes in which you jump in from somewhere else to j. Okay, so you were at time t, you were in a different state k. So this is your probability. Then within this time interval delta t, you jumped from k to j. And of course, the probability of that jump is given by this transition rate from k to j times delta t. Again, higher order effect. Okay, so this describes the effect of jump from k to j. And of course, there are many different k's. You have to sum over k. Good. Now, what you are going to do is clear. You divide everything by delta t. This goes away. This becomes delta t. This goes away. This becomes delta t. And you take the limit. Delta t goes to 0. And of course, this becomes the time derivative. And this goes away. This goes away. And you simply get this simple differential equation. And this is called the master equation. Now, I think it's clear. This is p dot. The time derivative of p is consists of this time derivative consists of two parts. This describes the escape from j to somewhere else, and this describes, jumping in from the state k to j. Okay, so this is a master equation, but I want to rewrite this by using something called a transition rate matrix. Okay, this is actually exactly the same thing and simply rewriting, and it could be tedious, but I think it's clearer to discuss this different notation to describe essentially the same thing. Okay, so R contains essentially the same information as this omega, but it's written in matrix form. Okay, so we define the transition matrix RT, which is a function of t, and it has jk. Jk runs from 1 to omega. And for j not equal k, so as for off-diagonal element, then rjk is simply this transition rate. But, this j and k switched. Okay, so this is from k to j, but if you recall the rule of matrix times a vector, this should be switched. Okay, anyway, so this rjk for non-off diagonal is basically the transition rate. And diagonal, as you can guess, is given by this transition rate minus the transition rate, which can be written, of course. This is just the definition. Okay, so this off diagonal is always non-negative, but this diagonal is in general non-positive. Okay, and from this definition, you see that if you sum over this first index, you get 0. So this is somewhat like stochastic matrix, but in the case of stochastic matrix, if you sum over j, you get 1. So in this case, you get 0 for any k. Okay, but this is the property of this transition rate matrix. In general, if a matrix, time-dependent matrix RT satisfies the two properties, one is that for off-diagonal element, it's non-negative, and this phi. if it satisfies these properties, then it's called a transition rate matrix. And of course, you can write down the corresponding transition rates. Okay. Anyway, so this contains essentially the same information as omega t. Okay. But anyway, with this notation, this master equation is simply written in this form. Okay. This term and this term can be unified into this simple form. And of course, this is the product of matrix and a vector. So this master equation is simply written in this very simple form. Of course, this is just a very simple ordinary differential equation written in terms of vector and matrix. And this is called a master equation in physics community. And in mathematics, this is called Kolmogorov's forward equation. But you rarely see this in math literature because they usually use something called backward equation. I'm not going to talk about backward equation, but in mathematics, this is called a forward equation. Okay, and of course, this is an ODE determining PT. So if you specify your initial condition, initial probability distribution P0, and solve this, then you get PT for NET. Okay, so this is the master equation. The solutions of master equation satisfies very interesting and important monotonicity, and suppose that PT and QT are the solutions of these master equations with the same transition matrix RT. Then you can easily show that the distance, the relative entropy of the Kullback-Leibler divergence of PT and QT is non-increasing in T. So this is the kind of distance between PT and QT. The distance never increase. It can decrease or it can stay constant, but anyway, can never increase. And actually, this is very easy because we have seen the monotonicity for stochastic matrix in page 19. And proof is essentially just rewriting. Okay, so let T be arbitrary and take very small epsilon. Then PT plus epsilon is P of T plus epsilon is given from this equation like this for small epsilon. Here's the collection. And if I denote by I plus epsilon RT, define I plus epsilon RT as T, then this is written like this. And I claim that this T is a stochastic matrix. First of all, if you sum over this first index, then you sum over this to get 1, you sum over this one to get 0. Okay, so this satisfies, first of all, the condition of the stochastic matrix, and it must have non-negative entries, but that's clear. First of all, off-diagonal elements are, of course, non-negative, okay, because this has non-negative elements. As for diagonal, this can have negative components, but this diagonal part of I is 1. So if epsilon is small enough, then the diagonal element of this one is non-negative. Okay, and we can make epsilon as small as we want. So we can safely say that this is a stochastic matrix. And of course, Q is written like this. And then we want to examine the time derivative of this, but it's quite easy. You take the difference, and then you use this. No. You take the difference. You use this and this, so you have this. Okay. And plus some small error. And now from what we have seen for stochastic matrix, this is non-negative. No, this is non-positive. This is non-positive. So this is upper bounded by order epsilon squared. You simply divide everything by epsilon and let epsilon 0 to get this. Okay. So we have this monotonicity. Okay. So this kind of suggests some convergence. But anyway, before talking about convergence theorem, well, this is just a side remark, but I want to discuss the notion called the probability current. And now I'm running out of some symbol. Current is usually called J, so I use this curly J to denote the current, and J is again index. Okay, for states. So I take two states J, K, and define this J, curly J, from J to K by this notation here. And this is really this is, as I say, the net flow of probability from J to K. Why is this? Well, this one shows that you are at you are at state J at time t, and then you jump from J to K. This says that you are at state K at time t, and you jump from K to J. Okay, so this is a probability flow of probability from J to K. This is from K to J. Okay. And clearly from this definition, if you switch J and K, you get something with minus. Okay. And now let's see what happens if you sum over this index K. Okay. Of course, K cannot be J. And you just go back to the definition and you sum. Okay. And here, as for the first term, K is contained only here. So you just sum over here, K. You just sum over all K, which is not J. But this is actually almost the definition of transition rate. Or you can go back to the definition of R, that if you sum over all this K, you get 0. Anyway, you see that this sum is equal to minus RJJ. And here you cannot do anything. You simply sum over K for K, which is not equal to J. But look, if K equals J, you get R minus RJJ PJ, which is exactly this. Okay? So this means that this whole thing can be written like this. This is simply the usual product of matrix and the vector. And actually, this is nothing but what we had in master equation. I think you remember. This is our master equation. So this is what we have. This is what we have in master equation. So we have this. Good. So this means that we have this identity, which is nothing but the very familiar continuity equation. Okay. We have seen in many places, in many places where you have a conserved quantity, the universal continuity equation holds. So in electromagnetism, there is a charge conservation, so you have continuity equation for charge and charge current, and in fluid mechanics you have mass conservation and you have continuity equation. In this case, we have conservation of probability, so we have this continuity equation for probability. Okay, so this is just a side remark. And now we come to the convergence theorem for stationary process. Okay. As I discussed, so we have this monotonicity, so this kind of suggests that there is some convergence in this case too. But in order to discuss convergence, we need to consider a special process, stationary process, which means that this omega J2KT transition rate is time independent. Otherwise, the condition of the system changes from time to time, so you do not expect any convergence in general. So we consider this only the stationary process. In this case, the transition rate matrix no longer depends on time. So we have time-independent matrix, our omega by omega transition matrix, transition rate matrix R. Okay, and the master equation is simply this. You don't have T here. And then this is a very simple ordinary differential equation, and it can be formally solved like this. So this is the general solution of this. Here you have e to the tr, but I think most of you know about this. This is matrix, but the exponent of a matrix is defined, for example, like this, by using this sequence, infinite sequence, or through this limit. You can easily show that this converges or this converges, and they give exactly the same result. And also you can easily prove that for a real parameter t, this e to the, if you differentiate this e to the tr by t, you get this. Well, of course, everything is what you expect from the ordinary exponential function. But anyway, this is a solution. Oh, of course, this is reminiscent of what you find for the usual ordinary equation. If you recall this simplest ODE, you know that the general solution of this is written like e to the t alpha times x 0, right? So this is a general solution, but This is quite similar to this. Of course, this is just a usual ODE for usual function, but for this matrix, no. For this vector and matrix, you have exactly the same thing. Okay. But anyway, before going to general discussion, let's look at a very simple example with two states, omega equal 2. And in this case, this is the most general form of transition rate, time-independent transition rate matrix. Alpha and beta are positive constant. And as you see, these diagonal elements are negative, and these off-diagonal elements are positive. And if you sum this and this, you get 0. If you sum this and this, you get 0. Okay, so this is a transition rate matrix. And the master equation for this case is simply written like this. So this is just a very ordinary, very standard coupled ODE. And actually, it's very, very easy to solve. You don't have to invoke this kind of thing. In this case, since P1 plus P2 equals 1, so you see that P2 is minus 1 minus P1. So if you plug this in, you get the very simple ODE, and you can immediately solve it. This is a solution. Okay, this is a general solution. C is an arbitrary constant, which is determined by your initial state. But anyway, if you examine the behavior of this, here's exponentially decaying factor. So if you let t goes to infinity, these terms vanish, and you see that this converges to this single probability distribution. Okay, so this C depends on the initial states, but this initial states dependent part vanishes, and you get this. So here's the convergence to a single stationary distribution. How general is this? Well, it's quite general, and as you expect, here is a beautiful convergence theorem. Okay. And again, this starts from a definition. So we say that a transition rate matrix R is irreducible if the condition is actually the same as what we have seen in the Perron-Frobenius theorem back in page 25. And this roughly says that any states J and K are connected through non-zero R. But anyway, let's look at this carefully here. So for any J and K which are not identical, there exists n, some number n, and a sequence of states, sequence of n plus 1 states, I0, I1, in, where I0 is equal to this starting point J, and In is equal to this final point K. And not moreover, in between here, these R connecting neighboring I's are positive, non-zero. Okay, so this means that you can go from J to K by only going through non-zero R or non-zero omega. So probably we should go back to here. So in this case, this irreducibility is satisfied. Okay, and now I'm not using R, but I mean here this is R31, this is R13. But anyway, in this case, for example, if you take state 1 and state 2, they are not directly connected, but it's connected. This one is connected to 3, and 3 is connected to 2. Okay, so in this case, this is the path. Or if you look at state 1 and state 7, then you can take this path to connect them, or you can take this path, or you can do something stupid. You can do something stupid and go like this. But anyway, there is a path. There is a path which satisfies this relation. Okay, so this is irreducibility, and that is satisfied in this example and in many physical examples. Okay, then here's the theorem. Assume that R, this time-independent transition rate matrix, is irreducible. Then, first of all, there exists a unique probability distribution PS, which is called the stationary distribution, that satisfies this. Okay? And so this said that this PS is the eigenvector of R with eigenvalue 0. Okay? And it holds that the components of this P is non-zero, positive for any J. And here's the convergence theorem. For any initial distribution P0, it holds that the time t infinity limit of pt, where pt is the solution of the master equation, is identical to this stationary distribution. Here's the simple picture. You start from your initial distribution and you solve the master equation, then it approaches here. You start from this probability distribution and again you solve the master equation, you approach here. Wherever you start, you finally approach PS, provided that your R is time independent and irreducible. And as I say that this is true in many physical systems. Okay, before proving this, I give an important remark about the H-theorem. The H-theorem is a historical name given by Boltzmann, Ludwig Boltzmann, long time ago. And here's the general H-theorem for our Markov jump process. Okay, and you can show that there is a function which knows the arrow of time. What does it mean? Well, so we suppose that R is time independent and irreducible. Then, so there is a unique PS. So I define a function of P called HP. This is not the Shannon entropy. I follow the notation of Professor Boltzmann here, but I don't use HP anymore, I think. So forgive me for using this confused notation. So anyway, I following Boltzmann, I define HP as this. Of course, Boltzmann didn't know this, but I define this. So this is a relative entropy, the Kullback-Leibler divergence between this probability distribution P and the stationary distribution PS. Then for any P0, HPT, where PT is the solution of master equation, this is now the function of t, but this HPT is no increasing function of t, and it converges to 0 as t goes to infinity. Okay. And this is, I think, quite easy because, first of all, we know that this PT converges to PS. So this means that since PT becomes PS, and since this is a distance, this HPT must converge to 0. And how about monotonicity? Again, it's very easy. It follows, from this monotonicity that we discussed in page 31. So in this case, we consider the two solutions of master equation. But now, in this case, PT is PT. But as for QT, we choose the stationary distribution itself. Okay. And of course, the stationary distribution itself is a solution of master equation, right? Of course, RPS is 0. So, and its time derivative is 0. So the special case of this is here. And then this is non-increasing in t. We already know this. So where were we? Yeah. So we get this non-increasing monotonicity behavior, and we also know that it converges to 0. Okay. So this is nice because we are discussing a very general Markov jump process, and our assumption is only mathematical that's about irreducibility, and we are not discussing any particular physics. But at this level of generality, we know that there is a function which knows the arrow of time, and there is some nice very convergence behavior. Okay. In part 3, we give more concrete discussion in the case of equilibrium dynamics, and in that case, we shall see that this HP is nothing but the generalized Helmholtz free energy. But anyway, it's nice to know that H-theorem, something like the H-theorem, is valid with this generality for general Markov jump processes. Okay, now the rest of this video is about the proof of this convergence theorem. And again, you may skip this part. And actually, it's not very interesting anymore. Yeah, that's true. Because the essential part, the most interesting part of the proof was already done when we discussed the convergence proof for this t to the n P0 case for stochastic metrics. Okay, and we do rely on this convergence theorem for stochastic metrics. Okay, so okay, let's continue. But sorry, I changed here. Okay, so I will discuss the theorem. So before I will discuss the proof of the theorem. So the essential lemma is this. For any positive tau, if you consider this e to the tau r, And then this is a stochastic matrix. And it satisfies this property, that is T of Kj is positive for any Jk. And then we can safely use the convergence theorem proved for this T in page 22. So anyway, let's go back to page 22. Where is it? Sorry, yeah, this is page 22. Okay, in this page 22, we have proved, we discussed this convergence theorem, and actually we did prove this theorem in an elementary manner. And here the condition, the essential condition was this primitivity for T. And primitivity said that there is an integer nu for which T to the component of T to the nu is positive for any Jk. Okay, so this is the essential condition. But now the statement of the lemma said that T of Jk is positive for any Jk. So this condition, this was satisfied with nu equal 1 in that case. So in that case, the primitivity of T, which is the only assumption in this theorem, convergence theorem, is satisfied. Okay. So let's go back to here. Okay, so this is where we were. Okay, so this is lemma, and I'm going to prove this. This is more or less trivial, but I will prove this in the next 2 pages. But anyway, let's suppose that lemma has been proved. Then everything is easy. So let's fix tau, and we need lemma for only 1 tau. And then we see that this T is primitive. And then we can use the convergence theorem for this thing. And then what we obtain is that there is a unique PS such that this is true. And if you recall this, this is equivalent to this. This is what we wanted. Now, so this, and now we already know the property of PS. So from this, oops, I think we have proven this part and this part. The only remaining part is this convergence part, but it's also very easy. For any positive T, write it in this way. So m times tau, m is an integer, positive integer, and some s, which is between 0 and tau. And now then P of T is written in this way, but this can be written by using this T like this. But now you see that if m gets large, if T goes to large, of course m goes. If T goes to infinity, m goes to infinity, and this converges to PS, right? And of course, if you apply this to PS, it doesn't change. Okay, so from this, you have seen that this for large T converges to PS. Okay, so the convergence has been proved. So the only remaining task is to prove this lemma. Let's do that. So the proof consists of 2 parts, and the first part is very easy. I want to show this sort of normalization for a stochastic matrix. Okay, and you want to show that if you sum this over k, you get 1. And so you can prove this in many ways. But for example, if you set tau to be 0, then this is just the identity matrix. So this sum is of course 1. And then you differentiate this sum with respect to tau, and then you get this drops. And then if you sum over k, then since this is a transition rate matrix, of course you get 0. So the sum is equal to 1 when tau equals 0, and it does not depend on tau. So you have proved this. Okay, and then you want to prove that for any positive tau and any j and k, this matrix element is again strictly positive. And if you have this and this, then we are done, because so we are going to show this, and we already know that it has a normalization of stochastic matrix, and of course everything is positive. So this shows this lemma. Okay, and actually, it's apparent that this part has been replaced. And before, actually, I had a kind of painful proof, and I didn't like that. And after that, I recently learned from Naoto Shiraishi this clever proof. So I decided to replace this. And actually, now Naoto has a book from Springer, and actually, but this does not appear in his book. But I think this will appear in the support page for his book. And I checked his web page, but it was not there. yet, but probably you live in future. You live in the future, so probably you can see its support page, and it should be there. But anyway, we want to show this, and the clever part of this proof is to first prove this statement for sufficiently small s. S is a S is something like tau. Okay, but anyway, let's start. So I start from the diagonal elements, and you replace tau by s, and you consider this diagonal element. And of course, this is just a definition of exponential. And since this converges, so you see that this is an real analytic function. So it's a continuous function, and I split this part and this part. So this start from order s. So this means that f is a continuous function of s, and this is important, f0 equals 0. Okay, and then no matter what this is and what sign it has, it's a real function. And if it's 0 when s equals 0, so you see you already have positive 1 here. So if s is sufficiently small, you see that this is strictly positive. Okay, so we prove this. You can prove this very easily. Now we do very similar things for off-diagonal elements too. So you take any j and k which are not equal. Then I claim that there is a constant n0 with this property. First of all, the kj element of r to the power n0 is strictly positive. But for any n strictly less than n0, this kj component of r to the power n is 0, vanishing. Okay, why is this true? So I recall the definition of irreducibility of R. Okay, so our R is of course irreducible, and this is the definition. For any j and k, there exists a path of length n, which basically consists of non-zero off-diagonal elements of R. This is a definition of R. So it is guaranteed that there is such n, and we take the minimum n with this property, and that is called n0. Okay, since this is minimum, in order to have non-zero this non-zero matrix element of L to the n0, you have to use all these. You have to simply multiply all these non-zero positive off-diagonal matrix elements and sum over different paths if there are many. Okay, so this definition and this choice of n0 guarantees this, and of course this. Okay, then the rest is very easy. So again, I consider this kj element where tau is replaced by s, and this is simply the definition. And because of these properties, this power series start from this one, s to the power n0. Okay, and this is strictly positive, and this power series again start from order s. Okay, so again you can call this something like gs, but anyway the argument is basically the same. Here you have an analytic function, real analytic function of s, and which goes to 0 as s goes to 0. When s equals 0, this is 0. Okay, so and this is strictly positive. So whatever this is, of course, this guy wins if s is sufficiently small, and this whole thing is strictly positive. If of course s must be positive here. So if s is sufficiently small, this whole thing is strictly positive. Okay, so we have seen this strict positivity for diagonal and all of diagonal elements. And then you just compare and take the minimum smallness and call it tau naught. So we can conclude that there is some very small tau naught, and if s is strictly positive and still not greater than tau naught, and this matrix element is non-zero. It's strictly positive. I'm sorry, strictly positive for any j and k. Okay, so this is only for very, very small, probably very small s, but it's not a problem. Okay, so we want to consider this for not general tau, which may be large, but this is just equal to this one, right? And then if you take this integer, positive integer n sufficiently large, this tau over n falls into this interval. So this becomes smaller than tau naught. And then you are sure that this has strictly positive matrix elements. And this is just a multiplication of matrices with non-zero, with strictly positive elements. So you have shown this. Good. So this lemma has been proved. And more importantly, we have proved this convergence theorem. Okay. So now we are treating very general Markov jump process with time-independent R with this irreducibility condition. But this irreducibility is satisfied in many cases, including this example, but not only that, many examples. And with this very simple condition, we do have this very strong convergence theorem, and it has been proved.